Hey everybody, good morning. It's Mr. Willis, and I'm going to talk with you today about combined gas laws and the ideal gas law. We're also just going to briefly review three of the other gas laws and how they form the combined gas law. All right, so let's go ahead and get started. Let's see. If we look at the first law we're going to look at is Gay-Lussac's law, and it tells us that the pressure of a gas is directly proportional to its Kelvin temperature. There's a few things that are important in here. One is directly proportional, and that means that they go in the same direction. And so Gay-Lussac's law tells us that if the temperature goes up, that the pressure does as well. Now, the other side to that is that if the temperature goes down, then the pressure does as well. And so the real thing about directly proportional is that they go in the same direction, either both up or both down. And that's true for temperature and pressure. Now, the other thing is that it's directly proportional to its Kelvin temperature. Most of the time, you will get your temperatures in degrees Celsius. Okay, let's just say 27 degrees Celsius. How do we convert that into Kelvin? We convert to Kelvin by taking Celsius and adding 273. All right, so in this case, if I took 27 degrees Celsius and added 273, that would equal, so that's degrees Celsius, and added 273, then that would give us 300 Kelvin. All right. And so anytime that we are doing any calculations in temperature, we must change to Kelvin. So first thing, change to Kelvin. All right? Definitely want you guys to remember that, and this is how we do that. So go ahead and write that down on your notes right now, that Kelvin is equal to Celsius plus 273. All right? Kelvin's equal to Celsius plus 273. There we go. All right. Just to reemphasize, if temperature increases, pressure increases. If temperature decreases, pressure decreases as well. Mathematically, we're going to say P1 over T1 equals P2 over T2. And that's going to be our pressure in atmospheres and our temperature in Kelvin. All right, and so as long as you know 3 out of the 4, so when you see something written in atmospheres, that is going to be pressure, and when you see temperature written probably in degrees Celsius, just add 273 to change it to Kelvin. All right? See, real quickly, Boyle's law. So here are equations for all three of our gas laws that we've looked at so far. Boyle's law, where V1 P1 equals V2 P2, and so as the those are actually going to be then inverses, meaning that if the volume goes up, then the pressure will go down. But if the volume goes down, then the pressure will go up. Okay, and so they are opposites from each other, and that's an inverse relationship. Be sure that you have that written down in your notes, that the volume and the pressure are oppositely related or inversely related for Boyle's law. They're oppositely related to each other. Charles's law, the volume and the temperature, and then Gay-Lussac's law, the pressure and the temperature, are both direct, meaning that if the temperature increases, the volume will increase as well if pressure is constant, and if the temperature decreases, then the volume will decrease. Again, if pressure is constant. What if pressure is not constant but volume is? Well, then as temperature increases, volume increases. Or excuse me, as temperature increases, pressure increases. And if temperature decreases, pressure decreases as well. So take just a second, pause the video, and be sure that you have those three things, those three sets of information recorded in your notes. All right? All right, and we will continue with, okay, and then there are the shortcuts that I just showed you. Boyle's law, oppositely or inversely related. Charles's law, directly related, both up or both down. And Gay-Lussac's law, also directly related, both up or both down. Let's take just a moment and talk about standard temperature and pressure. Standard temperature and pressure, you may read a question about gases, and it will say that one of the gases or a gas at one point in time is at STP. And when you see that STP, that means standard temperature and pressure. Standard temperature and pressure is 0 degrees Celsius and 1 atmosphere. Remember that when we convert that into moles, that it will be... Now remember that with our temperature, we are going to change it to Kelvin. So, so take Celsius and add 273, and that will give you 273 Kelvin. And so STP, while it is 0 degrees Celsius, it's also 273 Kelvin, and that's the temperature that we need to use. That is the units that we need to use almost all of the time. And again, our pressure will be in atmospheres, and you can look back at your notes from earlier in the week or from last week to see about the different conversions to atmospheres. All right, just something else to tell you, that 1 mole of any gas at STP has a volume of 22.4 liters. So 1 mole of any gas, no matter what kind, if it is at STP, will have a volume of 22.4 liters. All right, so please record all that information in your notes. Great. All right, the combined gas law actually takes all three of those and puts them together in one set of equations. And so if you have a gas that is changing conditions, so if you have a gas that is undergoing changing conditions, like the volume changes or the pressure changes or the temperature changes from one set of conditions to another, then we would use this law in order to evaluate the conditions either before or after the change. All right? So we would look at our volume either in liters or milliliters. We would look at our pressure in atmospheres, and we would look at our temperature in Kelvin. All right, so let's work a sample problem with that. All right, so calculate the volume of a gas at STP if 5.05 milliliters of the gas was originally collected at 27.5 degrees Celsius and 1.5 atmospheres. All right, now originally, so that means that these are all going to be my original conditions, or item 1. So here we have volume 1, here we have temperature 1, and here we have pressure 1. All right, so volume, temperature. Now let's see, this is 27.5 degrees Celsius. I'm going to go ahead and convert that to Kelvin, and that's going to be, I'm just going to add 273. So 27.5 plus 273 will be 300.5 Kelvin. All right, so we have that. And it says that it wants us to calculate the volume. Remember, this is going to be at condition 2. So this is going to be V2, and then at STP, which is going to be standard temperature and pressure. All right. So let's see. So I'm going to say V1 times P1, P1, let's just erase that real quickly. V1 times P1 over T1 equals V2 times P2 divided by T2. All right, so then we're just going to put the numbers in for that. And I see that V1 was 5.05. It's so important that you label these. If you will label them, then it is easy to plug in. But if you do not label them, you're really going to have a hard time. I knew that this was a volume because it says milliliters, and liters and milliliters are a unit of volume. So 5.05 for my volume. Now pressure 1. Okay, pressure, remember, is in atmospheres. Okay, and so I've got 1.5 atmospheres. And that is all going to be divided by 300.5. Now that's going to be equal to then V2, since I don't know that one, that is going to be the unknown, and so we will leave it as a letter. And then STP, remember that we just talked about that STP, the standard pressure, is 1 atmosphere, and the standard temperature is 0 Celsius, which is 273 Kelvin. All right, I'm going to take a moment and do the math, and I would invite you to do the same. Just pause the video. I'll tell you what, I'll just crunch the numbers while we're all sitting here talking together. So type in the numbers, and I'm going to type 5.05 times 1.5, and then divided by 300.5, and I'm going to get 0.0252. And that is actually going to be equal to V2 times 1, which is V2, divided by 273. Now, since these are divided, we will need to multiply in order to separate them. So I will take this number and multiply by 273. And when I do, I will get V2 of 6.88. Now the question is, what units? Remember that since my original volume was in milliliters, my final volume will be in milliliters as well. And so there's our answer, 6.88 milliliters. All right, take a moment, pause that, check it, see if you are able to get the same answer. All right, and then we will click on through and watch those things magically appear or disappear. The ideal gas law. Now, this is different from the combined gas law. The combined gas law functions if you have a gas that is undergoing changing conditions. The ideal gas law allows you to calculate unknown values from others under constant conditions, so at one point in time. One thing that's especially important for you to go ahead and record, is the value for R. It is 0.0821, and this only works if you have your volume in liters, your pressure in atmospheres, your quantity in moles, and your temperature in Kelvin. This is PV equals nRT, again where P is pressure in atmospheres, V is volume in liters, N is number of moles, the amount of gas in moles, R is this universal constant right here, so it is always that number, and T is in Kelvin, okay, our temperature in Kelvin. All right, so let's work a sample with that also. All right, And there we have the just the formula again with the reminder of what everything stands for: P for pressure, V for volume, N for number of moles. That should actually be lowercase. R is always 0.0821, and T, temperature in Kelvin. All right, so let's use the ideal gas law. Remember, the time when you're going to use the ideal gas law is if you have a gas that is only at one set of conditions. If you have multiple sets of conditions, then you should use the combined gas law or one of the other individual gas laws. All right, so let's see. It says calculate the pressure. All right, and so pressure is what I'm going to be finding. So I'll put it down with a question mark. Of this many moles, remember moles is N, it's our number of moles. So I'll put 0.412 moles of helium at 16 degrees Celsius. So my temperature is 16 degrees Celsius, and I'm going to go ahead and convert that to Kelvin real quickly. Remember that Kelvin is equal to Celsius plus 273, so I'm going to take 16 and add 273, and if my math is good, then 16 plus 273, let's see, 289. All right, so the temperature is 289 Kelvin, and occupying this much space. And so the amount of space that something occupies is volume, so that's 3.25 liters. All right, all of these are in standard units, moles, Kelvin, now that I've changed it, and liters. If they weren't, I would just need to make that change. So there are my givens, and I've already started part of the problem, and now I'm going to write down my formula. PV equals nRT. Let's see, P is what I'm looking for. V is 3.25. So if you have made this nice little list, then filling in the formula is super easy because you just do it from your list. 0.412 times R. I didn't write R down, so I'm going to look at the previous page. There we go, 0.0821. So let's write that down, 0.0821, and temperature, which is 289. All right, so again, I'm going to do do some quick math. 3.25 P will equal 0.412 times 0.0821 times 289, and go ahead and do the math for yourself. 9.775, and then divide that by 3.25, and I get 3.0. So the pressure will equal 3.0, and that's going to be in atmospheres. All right, thank you so much, and you have a couple of pages to practice with. Just remember that the combined gas law is when things are changing, and the ideal gas law is when a gas is just at one state or one point in time for finding out some unknown values. All right, I hope that was helpful, and good luck, help each other out, and we will see you next time.